Gaurav sir, should we start?
Yes, sir, we can start. Wait a minute, sir. Good afternoon, all. Good afternoon, one and all. On behalf of Country Jaipur, I welcome you each and everyone for FDP session. Vignan, Associate Professor from Department of Chemistry for the speaker profile.
Thank you, Gaurav sir. Thank you, Gaurav sir. So it's my great pleasure and honor introducing Professor Prabhakara Koya as our eminent speaker for today's FDP. He received his Ph.D. degree in 2005 from IIT Madras in the field of solid state and material chemistry. So after his PhD, he joined as a research associate at the Jawaharlal Nehru Center for Advanced and Scientific Research in Bangalore, where he worked as a research associate for 2 years under the guidance of Bharat Ratna Professor C.N.R. Rao in the field of material chemistry. So he was awarded a prestigious Global Center for Excellence in postdoctoral fellowship from Japan. And with the fellowship, he pursued advanced scientific research at the University of Tokyo, Japan. He also served as an assistant professor at the University of Kyoto, Japan in 2013, during the 2011 and 2012. In 2013, he joined as an assistant professor at Vignan Foundation for Science, Technology and Research in Andhra Pradesh, where he is currently a professor and head of chemistry division. Professor Prabhakara Rao has published 90 research papers in journals and conferences. Notably, many of his papers were published in very high impact international journals, and also his papers are appeared as a cover page in many journals. He also has 4 international patents in his credit and has written 2 textbooks. He has a total research citations of 800 with the H index of 13. So his new research findings on super hydrophobic porous material, which repels water like lotus leaves, has been attracted globally and highlighted in various international, national, and regional news media like Enadu, ABN Andhra Jyoti, Sakshi, The Hindu, Science Daily of USA, Material Gate from Germany. And also this work has been highlighted in the prestigious Nature journal. So his awards and achievements includes Best Reviewer Award from the American Chemical Society he received in 2016, both Research and Teaching Excellence Appreciation Award from Vice Chancellor, Vignan Foundation for Science, Technology and Research in 2017 and 2019 respectively. He obtained several research fundings, including 2 DST SERB fundings worth rupees 2 lakhs and 52 lakhs respectively. So his current research interests are porous coordination polymers and their applications, novel heterocyclic system, materials for gas storage and catalysis applications, nanocatalyst for polymerization and cyclization reaction, to name few. Today, he will discuss about his research work entitled Artificial Lotus Leaves for Application in Gas Separation and Oil Spills Cleanups. Please join me in welcoming Professor Koya Prabhakara Rao. Welcome, sir. Welcome, sir. And many thanks for accepting our invitation. Thank you.
Okay,
thank you, sir.
That my voice is good.
Now I request our Honorable Vice Chancellor, sir, for the special address to the participants.
Well, very good afternoon to all of us present here today.
I would like to once again extend a very warm welcome to Professor K. Prabhakara, a distinguished academician and a man of worth. The more you go through his resume, the more you feel gratitude for the Pratap University to have him here with us today. I am thankful to the School of Basic and Applied Sciences Department of Chemistry, Pratap University. Special thanks to Mr. Gaurav Sharma, the FDP coordinator, Mr. Pranit, who have been the instrumental in organizing such a wonderful faculty development program, the resource person of such eminence. He would be speaking on artificial lotus leaves for applications in gas separation and oil spills cleanup. Professor Rao, of course, as you've already been introduced, is from Vignan's Foundation for Science, Technology and Research, Guntur, Andhra Pradesh. So we welcome you once again, Professor Rao, and over to you for the faculty development program. Thank you so much.
So thank you, respected Vice Chancellor of Pratap University, for giving me this opportunity to introduce about my work. And moreover, I'm very happy to meet my friend, Dr. Pranit, after a long time. He has given me the opportunity to present my work in front of all of you. So am I audible?
Yes, sir.
Okay, my voice is good?
Yes, sir. It's good, sir.
Okay, thank you. I hope that you can see my slides also.
It's clear, sir. It's visible, sir.
Okay, thank you. So, good afternoon, one and all. First of all, it gave me immense pleasure to present my recent work, last 4 or 5 years, what we are doing in our lab. So, even though we are working a variety of fields of chemistry, but today I will be presenting one of very exciting work that has been highlighted all over the world, that is novel artificial lotus leaves for applications in gas separation and oil spills cleanup. I think this is a very important technology, not only for chemistry people, for almost all material science people also. So anyhow, I think I'm going to show you how it will be useful for technological applications also. So I have been arranged my talk in this following manner. First, I will be giving briefly 1 or 2 slides about what we are doing in our group, New Generation Materials Group in our university, group introduction, followed by, so what are these materials? So metallurgical framework, which is also called porous coordination polymers. I'm going to introduce about the topic, about this work, introduction about the work, followed by my results and discussions, and where we're using these materials applications. At the end, I'm going to give summary of my whole work. So let me start with my group introduction. So this is my group, New Generation Materials Group. So myself is a group leader. I'm having 6 PhD students. I think all of them almost from first year to 5th year are there. 2 awards has been already awarded from our university, doctorates. And basically, I'm working on these 4 areas majorly. Of course, small other works also I'm doing, but majorly these are the 4 works we are doing. First, organic molecular devices, where most of the work I have carried out this work in Kyoto University. That's where I learned. I'm continuing the similar kind of work in my lab. So basically, these materials will be useful for organic light emitting diodes or solar cell panels. So such kind of electronics and the chemistry combination of these work I'm doing on this topic, organic molecular devices. Whereas industry, so since they want to work a kind of drug design because most of industries are pharmaceutical industry. So that's why I'm working even design and synthesis of variety of starting from 2016 to 2020. And of course, my other work is recently started with collaboration with biotechnology and chemical engineering because ours also a kind of technical university. So most of the majority of the departments are technical education. So I want to collaborate with them so to get exciting materials which can be useful for potential applications also. So that's why I started other work that is nano and biomaterials. So very recently started, I published 1 or 2 papers in this area. We are planning to do some patents also in this area. And of course, today's topic that is porous coordination polymers, which also called metal organic frameworks, which is a major part of my research work since from my PhD and the postdoctoral with Professor CNR group. And later on, we recently, one of the highly reputed faculty that is Professor Susumu Kitagawa from Japan. So here I have published more than 20 publications. Even I have 4 patents also. Today I'm going to present on this kind of topic that is porous coordination polymers or metal organic frameworks. So first let me introduce about this. What are these porous coordination polymers? Because I know that some of you are very experts in chemistry and material science, but some of the students also are there. So who does not know about this area? Let me introduce even from the basics onwards. In materials chemistry, we know from many years, porous materials, especially inorganic porous materials, zeolites or aluminum phosphates, that's called alpos, mesoporous materials are known for many years, which are used as a gas separation, gas storage, especially mainly used for petroleum cracking and catalytic applications. In other sense, we also known from 20 years, carbon-based porous materials, especially carbon nanotubes, polarines, even though porosity is very less, but still it also serves as a porosity. The first base material that is pure inorganic, they're known for very rigid and strong strength-wise because they are mostly inorganic compounds, whereas carbon materials are known for flexibility. So by combining these two, why can't we mix it up together and make it a kind of hybrid materials that's known as porous materials or porous coordination polymers. In other words, we can also call it as metal organic frameworks. So here we have a kind of stable, very stable, rigid compounds like inorganic metals or metal clusters. Even we also have organic moiety, which can serve as a flexibility. So in this new kind of hybrid materials, so we can have both kind of advantage. So flexibility is there because organic moiety, and moreover, we can also have inorganic moiety, which can give rigidity to the materials. So this has been mostly working from last 20 years, majorly, even though known for many, almost 30 to 40 years, but it has been famous for many groups are working all over the world. And moreover, they have started using commercially also, especially in gas separation. And many companies also starting working on only metal organic frameworks. For example, my own boss, who is Professor Susumu Kitagawa, is also having his own company in Japan. Is working on in his company to making these materials and selling out the materials for various applications. Having introduced our topic, now how do we synthesize these materials? What are the important structures for any materials in material science? Along with synthesis, properties and structures are very important because structures can create very important properties which cause the important applications too. So I think all of I can start from very basics. We know that metals, so we have 118 elements are there, though most of the metals, especially transition metals, are highly coordinating to the ligands. We know that. So we take the metal and react with the ligands. So ligands where X can be a functional groups like very coordinating group like carboxylate or hydroxyl or phosphonate or sulfonic acid, which are highly coordinating ability. So these coordinating groups can have organic moiety and react with the metal and form this kind of variety of the structures. Okay. So So the structures can lead sometimes one-dimensional. What I'm meaning of one-dimensional is, so basically this is the inorganic moiety which are shown in the black color. It is extended only one direction. Where the red color one is the organic moiety, so which connects the inorganic moieties to give rise to a porosity. The porosity is here. And wherever if the inorganic moiety is two-dimensional, it is called two-dimensional compounds. Even though some cases the inorganic moiety can be three-dimensional also. They are called three-dimensional. Please keep that in mind that the extended frameworks here is basically based on the MOM extension. Means metal oxygen metal bonds extended whether one direction or two direction or three directions. But so most of the major application comes from now these materials with a kind of fourth kind of category, that is the coordination polymers. Okay, which is almost similar to complexes, but in complexes the extension will not be there, a simple metal and ligand. But whereas coordination polymers, it is the metal moiety can be simple one single metal or kind of cluster. So there is no extension. See here compared to here and here. Here there is no extension between the metal centers. There is only ligand. I mean, organic moiety is coordinated. There is no extension in organic, but that's the reason this is called coordination polymers. So simple organic moiety is very well known, or a simple aromatic, this kind of terephthalic acid, or maybe BTB ligand, or maybe dicarboxylic benzene, some kind of very simple moieties. More of these chemicals are very cheap, but when you're making the materials has huge applications. So that I'm going to show you some of the applications in coming slides. So keep in mind that in porous coordination polymers, there is no metal oxygen metal bonds extended. Only simple metals or metal clusters. It can be instead of one metal, it can be a cluster of metals also can be present. So it has, why this work has been attracted many researchers in all over the world, because of it's a huge number of applications. Some of the applications I also show you. So it has been used for gas storage. We know that recently very gas molecule storage will become very important after looking into the green cars, it means hydrogen cars. So we need to store the gas in a need not be cylinders. We can store in materials also. That's what our the gas storage. See here in this porous material, the gas has been stored. So not only we storing, we can also use for separation. For example, if you want to separate oxygen from various impurity gases like carbon dioxide, carbon monoxide, we can separate it using this kind of materials. Or separation of carbon dioxide from other gases, we can separate beautifully using these materials. And moreover, for separation, sometimes they are also using polymer membranes, but compared to polymer membranes, these metals are very cheap. Moreover, it can be reusable several cycles. That is the advantage over the polymer materials. And moreover, it can also use it as a catalyst for doing a lot of reactions. And moreover, it has other applications like one-dimensional materials or magnetic materials or optical materials, variety of applications as I have shown here. Okay. So since my work, my presentation is mainly for gas storage and separation properties, focusing on first three applications. Having said that, now let us show me that who are the pioneers of this work in the world. So even though this work has been started from almost 40 years back, but very recently, I mean almost last 2 decades, these three scientists worked a lot of variety of materials, especially Professor Koya from University of California, Berkeley. He has been known for creating very big, robust porous materials. Almost he achieved almost more than 16,000 meters square per gram. That's kind of very big porous materials has been discovered. Is known for big, robust porous materials. So, on other kind, Professor G. Ferret is from France. He is known for breathing effect. Means it is because of the flexibility of the organic moiety. Even though before when we enter the gas molecule, the materials, the size is very small. But when taking the gas molecule, it can also the size can also increase like a breathing. So such kind of behavior you observe Professor G. Ferre. Whereas third professor, Professor Susuba Kitagawa, who is my boss from Kyoto University, is known for functional coordination polymers, especially making a polymer materials by using inequal kind of metal organic frameworks or porous and coordinate polymers, which could not be synthesized by normal method. He achieved using this kind of functional coordination polymers. He is known for functional coordination polymers. Moreover, he also, from last, I think, 4 or 5 times, these 3 people have been nominating for the Nobel Prize. I hope that sometimes they may get Nobel Prize also in this area, because they are the pioneers of this field. So now the question is, so porous materials are known for many years, like MCMs or geolites or alpos. So what is so special about these metal organic frameworks or porous coordination polymers? One could ask the question. So see, for example, I'll show you some of the porous coordination polymers which has very unique behavior. For example, this is a material like the very simple ligand. This is a ligand they use, and they coordinate with the zinc metal or such kind of different metals. When they got the metal organic frameworks with this kind of speculated diagram, it shows that so these moieties, these wings, can acting as a gate opening and a gate closing phenomena. So whenever we want, it can open the gate just like a kind of machine, and it can enter the gas molecules. Whenever we want, we can close the gate. So such kind of behavior cannot be seen on other porous materials because of there is no organic moiety. So since here we have inorganic moiety as well as organic moiety there, we can observe very unique behavior of this kind of gate opening and gate closing behavior, which are very much useful for gas separation and gas storage applications. Whereas other very important example, see here, this another porous coordination polymer. You can see the porosity here, and which has a unique behavior. We can acting as a size selective. For example, here the porous size is very peculiar. Only that kind of reactants only can go inside of the pore, and more it can also acting as a catalyst to make a kind of chiral compounds. So we know that chiral compounds are mostly prepared by a kind of chiral organic catalyst, but there we cannot control the shape of the moieties, or we can control the size of the moieties. But using this kind of porous coordination polymers, we can have the catalyst behavior, and moreover, we can also have the catalytic active sites for making the unique chiral organic molecules. Whereas the other molecules, see, this is mainly useful in medicinal applications. We know that carbon monoxide and nitrogen radicals are very dangerous poisonous gases, but in small quantities, if you apply, you can treat the cancer. So medicinally proved that you can treat the cancer in very minute quantities. But how do we send very minute quantities to the patient? So very difficult to control the minute quantity to send the patients. But using metal organic frameworks, you can control it. See, for example, this example what I've shown you here. These are metal organic frameworks. You can control nicely releasing of the carbon monoxide or maybe nitrous oxide. So by applying some kind of photo energy. So whatever the amount we want, so that much the amount we can apply, so the same amount can be released, which can be very good control over the releasing of these gases, which has been proved medicinally that very good cancer treatment applications. Having said that, so now let us go to my work, what I have contributed, started with Kitagawa group, and I'm continuing the similar kind of work here also. So in fact, we started with one of the very known ligand, very famous ligand, that is BTB. This is the BTB ligand, very simple ligand, which has B3 symmetry, highly symmetric in nature. So this, by taking this ligand, we try to react with the metals, various metals, starting with the zinc or cadmium, because we know that why we have taken these two metals, zinc or cadmium, because the highly coordinating behavior. More zinc can accommodate any kind of coordination starting from 4 to 6. So whenever we have the flexibility in coordination, the materials can form very easily. So then we have started with taking this ligand and BTB ligand and kind of cadmium by changing the conditions, pH or acidic behavior. because conditions also very important when applying the hydrothermal reactions. The simple hydrothermal reaction, how we do is to take the ligand and try to dissolve in a solvent and take the metal salts and mix it maybe 1:1 ratio, or maybe we have to vary by trial and error method, because similar to organic chemistry, we cannot fix the quantities equally, because sometimes if you use the exact ratio, sometimes may not work it. If you change the conditions, we vary the metal to ligand, sometimes it works out. So we have to try first initially trial and error method. Maybe later on, once we optimize the conditions, later on we can synthesize in large quantities. Similarly, we try to control the conditions by varying it. We possibly should get two different kind of compounds at two different pHs. For example, if we use very highly acidic condition like pH 2, we got this kind of compound, which is a two-dimensional layer interpenetration, because the layers are interpenetrated to each other. And we can see that what the importance of this interpenetration is, we have very small pores. Sometimes small pores are also very important. We know that porosity is useful, but sometimes we need small pores, for example, especially for separation of the gas molecule. Whereas other one is three-dimensional kind of interpenetration. We look into these two compounds, entirely different kind of structures, and both of them are useful, very much useful for separation of carbon from other gases. If we send the mixture of the gases through the compounds, it can selectively absorb only carbon dioxide. It's very much useful for separation of the carbon dioxide, as I said you. So these metal organic frameworks or porous and coordination polymers are very much useful for separation of the variety of gases. For example, these compounds are useful for separation of the carbon dioxide gases from the other gases. In fact, this work has been highlighted, one of the most read article in one quarter. Okay, so by the same ligand, the same BTB ligand, then we are trying to react with other metal salts like lanthanides or actides, lanthanide groups, and F transition elements. Then we got very big porosity in this case compared to the previous case. See, you can see very big, robust porosity, and moreover, this can be absorbed variety of the gases. But based on the properties of the porosity, we can separate very beautifully methane from the carbon dioxide, methane from ethane. In fact, separation from methane from ethane is very, very difficult, because the size wise are very close to each other, and moreover, physical properties also very close to each other, because both of them are hydrocarbons. But you can able to separate them 100%. So you can see the breakthrough curves of this compound with and treating this mixture of the methane and carbon dioxide. You can separate 100% of the methane from the carbon dioxide, methane from ethane gases. So this has been published in Advanced Functional Materials, one of the highly reputed journal, and moreover, this work has been highlighted as a kind of front page. Front page has been highlighted this work. And so the major problem with the previous two cases is we got very beautiful compounds, but the problem, one problem what we face is those compounds are highly hygroscopic in nature. You know that what is the meaning of hygroscopic? Because when you put it outside, it always absorbs moisture. But that is one of the drawbacks of those materials. So then we thought how to overcome these problems of hygroscopic or maybe water sensitive compounds. Then we thought, why can't we design our own ligand by changing the properties of the ligand? Then we looked into the structure of the what ligand we used earlier. This is the ligand what we use, highly symmetric, D3H symmetry. But we know that highly symmetric in nature, we know that it has highly hygroscopic nature. If we reduce the symmetry, so maybe sometimes we can reduce the water absorption properties, means it can be water sensitivity can be removed. So then what we have done is we changed whatever the carboxylic group at para position, we change it to meta position, so that we want to reduce the symmetry. So whenever this ligand reacted with metals or metal centers, what we are expecting is it should be a water, it cannot be react with the water, or maybe we can say that hydrophobic nature. So as per our expectations, so after synthesizing these ligands with some of the methods, what I am not going to show you because that organic methods that I am not going to show you here only because this talk is only materials purpose. You can read my paper, you can understand how to synthesize this ligand. So this is the synthetic methods what we applied to get very novel superhydrophobic, or you can say that artificial lotus leaf. We have taken the ligand, and what are the ligands I showed you in the previous slide. This is the ligand we have synthesized. This ligand we have synthesized, and then we put up these hydrogen bombs. These are called hydrothermal with Teflon and stainless steel. We put up those things in and these things and dissolve in DMF and mixture of the solvent DMF, methanol, and water. Then we close the cap and we heated hydrothermally in furnace about 100 degrees of the temperature over 4 days. Then we got very beautiful crystals, as I showed you here. These are very beautiful crystals. And of course, the crystals also solved by single exercise study. One of the disadvantages of inorganic chemistry is unless until we solve the structure, it's very difficult to know the structure of the compound. Yes, but organic compounds, we can have very beautifully by NMR itself, we can able to deduce the structure, but inorganic compounds is difficult. That's why we need to have a single crystal structure. So this is a beautiful single crystal structure. It's entirely different to the previous structure where what we got it because they are highly symmetric in nature. Even though porosity is not very big amount, very small porosity, only maybe 8 by 10 aperture. So, but very important one is so what we, as per our expectations, we found actually we are expecting is a hydrophobic in nature, but to the surprising to us, even it becomes super hydrophobic. What is the meaning of super hydrophobic? I will tell you in the coming slide. So hydrophobic and super hydrophobic metals I will be explaining with the introduction. See very beautifully when you put a water drop similar to your lotus leaf, you put a water drop, you can see nicely a water drop. But in most of the materials, you put a water drop, even it may not absorb, but it cannot stay as a water drop, similar to your hydrophobic behavior. Even in crystals, or even after removing the solvent molecule, because here my solvent molecules are there, even after removing the solvent molecules or powders, whatever the phase we are going to use, it still is a very good super hydrophobic in nature. So it's almost behavior like a lotus behavior. I think lotus, all of you know that. So we have taken lotus leaf and put in a water drop, it behaves like a water drop. The reason because of it is a super hydrophobic nature. So in coming slides, I will show you what is super hydrophobic, how many types are there of the super hydrophobic, which some of them may not be knowing the basics of the super hydrophobic materials, maybe artificial lotus leaf. I will show you in coming slide. Of looking into the structure, what we can give conclusion that this is the ligand and this is the metal centers. They are arranged in such a way that it is close to the reverse micelle structure. Reverse micelle means the polar groups are inside and lengthy alkyl chains are hydrophobic chains are outside. So whenever you put water drop on this kind of reverse micelle, the water drop will be staying here. So it always because of hydrocarbon moieties, the water drop will not go inside. So almost our compound also almost similar kind of structure. So that's the reason why we thought that maybe a corrugation means not uniformity. Moreover, hydrophobic moiety is exposed to the layers, give rise to these super hydrophobic materials. In fact, this is the unique behavior. Earlier, super hydrophobic mobs are known, but the main problem is they modified the surface using fluorocarbon moiety or maybe length alkyl chains. If we introduce the length alkyl chains here, the porosity will be lost. But here in this case, without modifying any surfaces, directly we got these super hydrophobic materials. That's the reason why this work has been highlighted by Nature 1 week as a kind of sponges which can repel the water. So in fact, so as I told you, some of you who do not know about what is super hydrophobic material means. So if you take any surface, this is a surface, you put a water drop like this. If the water drop contact angle means angle between the this one and this one, the contact angle means like this. If the contact angle is less than 90, that is called hydrophilic, means they are always like the water. If it is the contact angle is between 90 and 150, that is called hydrophobic material. The contact angle more than 150 degrees are super hydrophobic, means highly repels the water. So two types of super hydrophobic materials are known. So one is Wenged model and one Casey-Baxter model. What is the Wenged model means? Actually is kind of waxy behavior, permanent kind of super hydrophobic materials. Means here we have a liquid phase, here we have solid phase. In between there is no other phase. So basically the compound itself don't like the water. So that is the reason why these materials behaves like a waxy nature, soft nature. See, for example, for this one is rose petals. I think morning if you go and see near the rose tree, we can see that some drops of water will be there on rose petal because this is a kind of pendulum model of the soft nature. Even if tilt the rose petal also, still the water drop is still sticking to the water. Okay, because highly attraction between there, this water and the rose petal. That is the reason you tilt the petal also. Still, water drop can be attracted to the petal. There are other model that is called Cassie-Baxter model. Here, somewhat different. So this is the solid phase, and this liquid phase. What we are going to put in the water drop, and in between we have a kind of gas phase is there, where we can see gas molecules will be lying in between of these that small holes. So that's why we got three-phase kind of compounds where we have liquid is there, gas is there, and solid is there. Three-phase kind of components. Okay. So what happens now if you put the liquid here? So this is a solid. What are the gas molecules are in between of these kind of pillars? It will not allow the water to settle on the solid material. That's why it acting as a superhydro behavior. The example for this kind of material is a lotus behavior. So we take a water drop and lotus, we put in a water drop and lotus behavior, water drop only. So this is also called self-cleaning phenomena. Just it is opposite to this, means if it just a little bit angle you make it, the water drop immediately go off. It cannot be sticking to the leaves. That is the reason why if you put a water drop here, it cannot stay here. It go down. It go to the center because highly self-cleaning behavior. Self-cleaning means it remove the water, try to haste the water. So where do we use these materials? I think sometimes once in a while we used to see in news channels. So a lot of oil is spilled in a kind of sea, Arabian Sea, because of ship broken or so such kind of things. What happened? Such kind of oil is very difficult to remove it because a huge amount of the oil, and moreover, a lot of seawater is there. Very difficult to separate it, and moreover, that is very dangerous for the environment also because around such area, so no sea animals can live. So it become problematic for the environment. We have to remove such kind of oils. Very problematic oil. These materials are very much useful because we know that these materials are hates water, but it likes oil, so almost opposite to that water. So such kind of places you just put it the compounds and collect it because it cannot go down to the water because you know that it hates water, and we don't absorb oil. You can cut it very easily. Later on, we can remove that oil from the material. And not only this, we have so many applications. For example, self-cleaning cloths. I think in the markets already is there self-cleaning cloths. So just we go to the rainy day on rain, so it's not wet because we are coated with such kind of materials because it hates water. And moreover, painting on the cloths or maybe painting tiles. So such kind of materials have been known for these applications. So huge number of applications are there for this using superhydro materials. Having said that, definition of what is superhydro materials are artificial lotus leaf. So even though we are very successful synthesizing materials, we want to explore many such kind of materials. What we are doing, we are taking the same ligand, we try to react with other metals, various other metals. So fortunately, unfortunately, we don't know, but we could not able to get any compounds other than only one compound what we got,